Okay, so next exercise 24. So far we have seen groups of matrices where the elements were real numbers. But now we are going to see matrices where the elements are coming from finite number systems like integers mod 2, where the entries are actually not numbers but congruence classes modulo 2. So you already know that these integers mod 2 form this set J2, which has two things. They are not numbers, they are sets. Okay, the first is the set of all integers which are divisible by 2, and the second is the set of all integers which leave the remainder 1 when divided by 2. So in other words, this is the set of all even integers, this is the set of all odd integers. Each one of these entries is any one of these two things. Okay, now using these matrices, and one extra condition is given, AD minus BC is non-zero, that is the determinant is non-zero. Now in this context you have to understand that this 0 is that 0, the set of all even integers, the 0 element in J2. Now using matrix multiplication as the operation in G, we have to prove two things. One of them is that G is a group, and the other thing is that G has order 6. So unlike the previous matrix groups which were all infinite, these are going to be finite groups. This one and the next two exercises that are coming after this. So let us see how we can write the solution. The first part of the question, actually we don't have to do anything. We have seen in example 9 that if we consider such matrices with this restriction, that these are non-singular matrices, that is the matrices where the determinants are non-zero, and the entries are not coming from J2 or any other thing, but any specific thing, but in general from the set of all integers modulo P, where P is a prime, then under matrix multiplication the corresponding system is a group, and this is true for any P. So in this case we just have P equal to 2, that's all. So we already know that this system forms a group. So the only thing we have to do is that we have to prove that it has order 6. So that's what we need to do. However, let us first mention that we already know this is a group. The group G here, or okay, not like this. We can't say the group G, that's what we have to say why G is a group. G is the group in example 2 to 9 when P is equal to 2. So from there we know that G is a group. Now we have to count the number of elements in G. We are given this restriction. So the strategy for counting is this. First we count the number of possible matrices without any restriction. Then from that number we are going to subtract the number of matrices where this restriction is not true, that is where we have AD minus BC equal to 0, or where we have AD equal to BC. So that will give us the number of matrices in G. Without any restriction, the number of matrices of this form where A, B, C and D are in J2 is 2 to the power 4, which is 16. But why? You see, if we don't have any restriction, then each of these entries can be chosen independent of the other entries. And since J2 has two elements, so each one of them can be chosen in two ways. So in total there will be 2 to the power 4, that is 16 ways. The equation AD equal to BC has the following solutions in J2. Okay, now we have to figure out in how many ways we can have this true in J2, AD equal to BC. That will that number of ways has to be subtracted from 16 to give us the number of elements in G. Now keep in mind that in J2 means these things are coming from J2, and then we have to see how we can have this. Now this can be had in two distinct ways. Either both sides are equal to the congruence class 0, or both sides are equal to the congruence class 1. Now first we look at the 0 case, when AD and BC are both congruence class 0 modulo 2, and that can happen in this way, in these ways. A, B, C and D, all of them can be 0. That is one way. Okay. Another way is that AD stays 0, that is A and D are both 0. B is 0, C is 1. That is another way. Then we can have this also. B is 1, C is 0. Okay. And then if we interchange the places of these equations, we can get two new solutions. Now B and C are 0, A is 0, D is 1. Or A can be 1, D can be 0, and B and C are 0. That is another possibility. What else? We can now get rid of this 0, 0. We can have 0, 1, 0, 1. Or we can have 0, 1, 1, 0. Or 1, 0, 0, 1, and finally 1, 0, 1, 0. These are the ways in which both sides can be the congruence class 0. However, both sides can be 1 also, and there is only one way of having that. And that happens when all of these 4 variables equal the congruence class 1. So these are all the possible solutions of this equation in J2. So let's now count how many of them are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hence the number of matrices A, B, C, D where these are in J2 and AD minus BC is not equal to 0 is 16 minus 10, which is 6. That is, order of G is 6. So that's how we have that G is a group of order 6. Since the number system from which the entries are coming is finite, so there are only finitely many matrices possible. From among them, we have chosen some special matrices, namely the non-singular ones. Let us next look at another exercise like this. I think I need ink. So the next one has two parts, two subdivisions. 25. It takes some time for the ink to appear. Anyway, let us just start and we will see when it comes clearly. A. Let G be the group of, okay, so the beginning is almost just like the previous one. What the hell? Let G be the group of all 2 by 2 matrices A, B, C, D, where again AD minus BC is non-zero, and now these entries are integers modulo 3. In the previous one we had 2, so now they are coming from J3. Relative to matrix multiplication. So we already know, and here they have said also that this system is a group. So that's not the question. The question is its order. Show that order of G is 48, and there is part B also. If we modify the example of G, in part A, by insisting that AD minus BC be not just non-zero but specifically 1, then what is order of G? So here we are working in the number system J3. So from our experience with the previous solution, we can straight away start like how we did in the previous one. Why do I keep forgetting these things? This is part A. The number of matrices, I should have written without any restriction, but we understand. We can just simply write like this also. The number of matrices A, B, C, D, where the entries are from J3 is, okay, now for each one of these entries we have 3 possibilities in J3. These congruence classes, keep in mind, I am saying it again and again, and I will probably say it even more when we study field theory, that although we are using the same notation for these congruence classes, you should keep in mind that they are different things. These two are not the same thing. This is the set of all even integers. This is the set of all integers divisible by 3. So you have to be careful in which number system you are working, and if you are having two different number systems in the same situation, then you better use some other symbols to distinguish between these things. Here, however, we have no need, just saying that we will be using these things, but you don't forget that they have a different meaning than what they had previously. So each of these entries has 3 choices. So in total we will have, there are 4 entries, so 3 to the power 4 equal to 81 possible matrices. Now from among these possibilities we have to remove those where we have AD equal to BC. For that we now calculate not the number of ways, the ways of, or rather let me write like this. Sorry for these interruptions, but let us just have the language properly. We can have AD equal to 0 in the following ways. Okay, in how many ways can AD itself be 0? Clearly both of them can be 0, or the first one stays 0 and the second one is 1. The first one is 0, the second one is 2. The first one is 1, the second one is 0, and the first one is 2 and the second one is 0. So these are all the possibilities in which just AD itself can be 0. Okay. Just like that we can have, but apart from being 0, AD can be 1 also or 2. We can have AD equal to 1 in the following ways. Of course, both A and D can be 1, then AD will be 1, or both A and D can be 2. How do we have this? Because you see, by the definition of multiplication of congruence classes, this will be 2 times 2, which is 4. And we already know that 4 is congruent to 1 modulo 3. So, besides 4, we also have 1 in this congruence class. So, instead of choosing 4 as its representative, we can choose 1 also. That is, it is this congruence class. And AD can be 2 also. We can have AD equal to 2 in the following ways. This can also be only, there are 2 possibilities. One of them is 1 and the other is 2. Two possibilities. And this is only for AD. Similarly, we have BC equal to 0 or 1 or 2. Okay, now we try to figure out how we can have AD equal to BC. The number of ways of having AD equal to BC equal to 0 is, okay, now AD can be 0 in how many ways? 1, 2, 3, 4, 5. In 5 ways AD can be 0. BC also, independent of AD, can itself be 0 in 5 ways. So, together they can be 0 in 5 times 5 equal to 25 ways. The number of ways of having AD equal to BC equal to 1 is, here how many? It can be 1 in 2 ways. Similarly, BC itself also can be 1 in 2 ways. So this is 4, and finally the other one will also be 4. Is also 2 times 2 equal to 4. So the number of solutions of AD equal to BC, total number of solutions in J3 is 33. Okay, this implies we are no longer going to write again number of matrices, this and that. We straight away write order of G equal to 81 minus 33, and this is 48. So that's how we get that G has 48 entries. Not a small number. You see, if someone wants, they can list all the entries, but there will be many, 48 different matrices, where in each one of them the determinant is non-zero. Okay, now we go to part B. Is it correct? Yes. Now in part B, we are asked to calculate the number of matrices where AD is equal to AD minus BC is equal to 1. Okay, so we can make use of these calculations. The equation, but before we do that, the equation AD minus BC equal to 1, or since we are writing using these notations, we write like this. In J3 has the following solutions. Of course we can, or let us start like this. And 2 minus 1 is equal to 1. How? These two we clearly understand. This one, however, if you calculate the left hand side, you get the congruence class minus 2. It may seem strange at first, but keep in mind that in place of the representative of a congruence class, we can take any of its elements, and congruence classes contain integers, so sometimes they can be negative, sometimes means most of the times they can be negative also, but this is equal to 1 because these two things are related by the relation congruence modulo 3. Minus 2 is congruent to 1 not 3. That's why we have this. Okay, so these are the solutions, possible solutions. Now we see how we can have AD equal to 0, BC equal to 2, those things. Hence, the number of ways of having how can we write it? Okay, let's write it like this. AD equal to 0 and at the same time BC equal to 2 is, in how many ways we got 0? In 5 ways, see, and 2 can be had in 2 ways. So if we choose them independent of each other, then the total number is 5 times 2, 10, just like that. The number of ways of having AD equal to 1 and BC equal to 0 for this equation, the second one, is same. This is 2 times 5, 10, and finally the number of ways of having AD equal to 2 and BC equal to 1 for the last equation is 2 times 2, this is 4. So the total number of solutions of the equation AD minus BC equal to 1 in J3 is 10 plus 10 plus 4, which is 24. So you can see that this is half of what we had previously. That is, in this case, order of G, is it really G? Yes, it is G. G, but with the modified condition that AD minus BC now has to be 1, is 24. And we come to the final exercise in this set of exercises. Now this one is going to have a general prime instead of 2 or 3. So these gave us some practice. We were able to formulate some strategies for calculating these things, but now we have to tackle the general case. And it's just like what we have in this exercise, in the 25th one. Since it's general, it's also accompanied with a star. That is, it is supposed to be somewhat more difficult than the usual ones. Just like the previous one, here also we have 2 cases. Let G be the set of all 2 by 2 matrices A, B, C, D, where A, B, C and D are integers mod p. P a prime number, any prime number, such that AD minus BC is not equal to 0. The rest is same, only we have a general prime. G forms a group relative to matrix multiplication. We already have seen why it forms a group in the 9th example in section 2.0.